Hello everyone, my name is Chen Jian. Today we are going to introduce our work, Azimuth-invariant multi-view three-dimensional object detection. This work is in collaboration with Zhejun, Yujie, Xiangxiang, and Ma Lin. In this paper, we propose an azimuth-invariant detector, AeDet, which is able to perform azimuth-invariant object detection. Specifically, the BV features in multi-view three-dimensional object detection are naturally endowed with radial signals. To preserve the inherent property of the BV features, we propose an azimuth-equivariant convolution and an azimuth-equivariant anchor. The proposed convolution can run azimuth-invariant BV features, and the proposed anchor enables the detection head to run predicting azimuth-invariant targets. Generally speaking, a popular LSS-based multi-view three-dimensional object detector, for example, AeDet, consists of an image view encoder, a view transformer, a BV encoder, and a detection head. The image view encoder extracts the high-level features of the multi-view images. Then the view transformer transforms the image features from the image view to BV according to the predicted depth. Finally, the BV encoder further encodes the BV features, and the detection head predicts the bounding board of the object. Assume the same car precisely faces different view cameras with the same distance at different time steps, and the cameras capture the same imaging for the car. These images would be transformed to be the rotation equivalent BV features in different azimuths by the image view encoder and the view transformer. However, the existing multi-view three-dimensional object detectors use the typical two-dimensional encoder and the anchor-free detection head to perform BV perception. Such design ignores the radial signals of the BV features and generates different features and predictions for the same bars in different azimuths. Here we analyze why these object detectors cannot generate the same results for the z bars in the different azimuths. The first problem is the typical convolution applies the same sampling grid at each location of the features. It would sample and produce different BV representation even for the same imaging in different azimuths. The second problem is the angle-free detection head directly predicts the object orientation and velocity along the Cartesian coordinates, which would require the detection head to predict different targets for the same imaging in different azimuths. For the first problem, we propose an azimuth-equivariant convolution to unify the representation learning in different azimuths. Specifically, we rotate the regular sampling grid of the typical convolution to a rotated version according to the azimuths at each location. Then we adopt the convolution operation based on the new sampling grid and extract the azimuth-invariant BV feature. For the second problem, we propose a new azimuth-equivariant anchor to unify the prediction targets in different azimuths. Specifically, we define an azimuth-equivariant anchor according to the azimuth at each location. Then we could compute the Boss residual based on the azimuth-equivariant direction using the azimuth-invariant prediction target. In addition, we introduce a camera-decoupled virtual depth to unify the depth prediction and generate a precise BV feature. We first leverage a camera-decoupled depth network to predict a virtual depth based on a virtual focal length. Then we map the virtual depth to the real depth according to the classic camera model. Such design enables the depth network to focus on modeling the relationship between the image feature and the virtual depth, regardless of the intrinsic parameters of the camera. Here we show the framework of the proposed AeDet. It first predicts the real depth according to the virtual depth and transforms the image features to the BV feature. To preserve the radial symmetry of the BV feature, AeDet encodes the BV feature by the AeConf-based BV network and predicts the detection results based on the Azimuth-invariant anchor. We show the BV features and prediction from AeDet. AeDet used almost the same feature and prediction for the Z bars in different azimuths. To demonstrate the effectiveness of the proposed methods, we apply them to BV depth. The azimuth-invariant evolution and the azimuth-invariant anchor improve the MDS from 44.2% to 46.2%. The camera decoupled depth network improves the MDS by 1.2% comparing to BV depth. The detection robustness to different azimuths is important to autonomous driving system, since sometimes the vehicle may turn a large angle. To verify the robustness of the detectors, we propose a revolving test by turning the vehicle 60 degrees clockwise and predicting the rounding bar in the revolved view. BV depth generated a worse result in the revolved view, while AeDet used almost the same prediction in both views. On the nuisance validation set, AeDet outperforms the most common multi-view three-dimensional object detectors by a large margin. On the nuisance test set, AeDet set a new state-of-the-art result. For more information, please refer to our paper. Thank you.